There we go. Welcome to Cohort 2 webinar on logarithms. Before we get into logarithms, there is the usual bit of theory, a little bit of theory. Today, just talking about, my favourite subject, attitudes towards maths, on which I'm writing my whole dissertation. And we've talked about this before, really. It's just about challenging attitudes towards maths and how to do that. So, in the UK and in the US as well, they find this. It's fine to say that you're bad at maths, and it's not cool to be good at it. I think perhaps the not cool issue isn't so bad. I mean, it does come across still as a nerdy subject. But I'm not sure that maths specifically is any worse than, if you're a hard worker, you're going to get called a nerd or whatever. And it's considered often difficult and boring. And, that you have to be really clever. And so people sort of have this fixed boundary issue. They're thinking, okay, well, I can't do it. So in terms of how has this happened, it's arisen out of a number of ways, from the fact that it's taught traditionally in a very, it was traditionally taught in quite a boring way, which led people to sort of be bored by that. But it's also about, what you believe about ability. So this is where we're talking about what I've talked about before. Carol Dweck has identified that people either have a fixed or a growth mindset, and they think that in the UK, 40% of people have a fixed mindset about maths. I'm surprised it's that low, really, but supposedly that's what they think. So people with a fixed mindset believe you are born with a certain amount of intelligence, and either you can or can't do something. So they believe that you are naturally talented. So those sort of people, unfortunately, Will, can you just mute yourself, please? People with a fixed mindset about maths believe that they expect it to come naturally to them. So as soon as they come across something they can't do, they're like, oh, it doesn't come naturally to me, so I can't do it. They don't realise that they actually need to increase the amount of effort they put in, or ask for help, or practice it more. So they're not very good at persevering, and reach basically a fixed boundary beyond which they don't push it. They think that's their limit. Whereas people with a growth mindset believe that they are in control of their situation. So if they want to, understand something, if they're struggling with something, they just need to work harder or apply yourself in a different way in order to sort of grow your intelligence. So struggle is necessary to learn, and really this has to start from a very young age with small children, not doing everything for them and letting them struggle through things. It's hilarious, actually. My daughter came back the other day and said, I'm going to persevere today. We've been talking about perseverance, and even used those words, and then spent ages building a massive train track, which she was struggling to do. So it's obviously getting all the way down to primary school, which is great, but just seems to be forgotten when faced with maths, where there's math tests. It's come on, quick fire, do it quickly. And people get the impression, well, if I can't do it quickly, then I'm obviously not very good at maths. And because maths involves, a lot of tricky concepts, different symbols, you have to really think about it. Everyone hits that wall, and it's just about whether you push through it. And it's very important about praise and how to praise kids. So if you're saying to kids all the time, oh, that's really clever, well done, then when they can't do something, then they think they're not clever. So they stop trying. It's all about expectation and reward. So having a mindset and this attitude towards maths impacts massively on your motivation and engagement, and if you're not engaged, then you're just not going to get anywhere. Whereas with a growth mindset, you can't know everything. Being clever is not what it's about. It's about, okay, I haven't learnt it yet. So in terms of praise, and it's okay, I can't do this, you say, yes, you can't do it yet. So there's a lot about how we talk about things, and a lot about how we present maths, so that it's not perceived as boring and difficult. So not making it a race all the time and that sort of thing. Particularly with the kids who have this to the extreme. I mean, a lot of kids don't like maths, think they can't do it, and actually those two are linked, aren't they? Because if you think, generally at a young age, kids like what they can do. So if they can't do maths, they think, and they don't like it, and they just switch off. Some kids have extreme reaction to maths, which basically becomes an anxiety. And it's one of those things, isn't it? You should see my desk at the moment, and the whole room is a complete pit, and which is always an indication that I've got too much on my plate. And it's that same thing with maths. It builds up and builds up and builds up until it just seems like too much. And you've got to just go back to the beginning and start again. So if you get to the point where you're at secondary school and you've still not understood fractions from primary school, you're going to struggle. And then you think that you can't do everything. And every new topic that involves that, you very quickly overwhelmed by. And that feeling of being overwhelmed means that you're basically just, I think your amygdala is trying to get you to run away at full pelt. But it's an actual anxiety. And kids with math anxiety, you sort of have to deal with slightly different way, by sort of dialing it back really, and really building on their self-esteem, building up their self-esteem first before you try anything difficult with them. They're the sort of kids that would really benefit from, quiet tutoring on the side or some sort of intervention really. Anyway, so that's just sort of to say that as a teacher, I mean, you come across a lot of teachers where especially with primary school teachers that I've come across who've sort of said, oh yeah, I hate maths, So they are already embodying that feeling and they are teaching our kids. So then when we get them at secondary school, they've already had from their parents and from teachers all these messages that maths is hard and boring and not something to enjoy, and they have the wrong attitude. And before you can get them to do anything, they have to have the right attitude. So you just need to embody that, and I'm sure you guys do anyway, because you just have to have that, oh yes, I enjoy this, it's all good, find something like that. I mean, there are topics that we all go, yes, I know, we've just got to get through this. I don't like this either. But hopefully that's few and far between. So in order to change that attitude, and if you've got a class which is just the whole class, I mean GCSE resit classes, if you ever are in a sixth form college or FE college where you're having to do resit classes, I would say spend a good 3 weeks doing this rather than getting them started, because the same slogging through the same work again, you'll find that most of them fail GCSE because they have the wrong attitude or some sort of learning disability. So Carol Dweck has developed a whole program called Brainology, which is all about changing mindset, and it's just about teaching them how the brain works and using praise. And I don't know if I sent all of you, but I sent some of you my intervention that I've written, doing that sort of thing. But it's just about getting the kids involved in their own learning. So I think you start by talking to them about how their brain works and how they learn and all of that before you start teaching them any math if they're that sort of class. So really good book for kids, for teenagers, is The Straight A Conspiracy. The Growth Mindset Handbook is really good for teachers. It's got little, that's a really sort of like little cheap, tiny book off Amazon that's quite good. And then Growth Mindset Math is, I think that's Helen Hindle's website, which has got loads of resources linked to the National Curriculum and loads of references. Anyway, let us get on to some math. I'm just going to unmute you, Adam, so that you need to mute yourself, just in case you want to talk. Right. Logarithms related to exponentials, because they are basically the inverse of exponentials. This comes up at AS in Core 2, generally, depending on the exam board. But students are expected to know about exponentials, exponential graphs. So an exponential y equals a to the x. We'll talk about that in a bit. Understand the relationship between logarithms and indices. So indices, powers, exponents is another word for it. So an exponential, you know what it is. It's something that has good power. Use laws of logarithms, solve equations, understand the properties of natural ones. Now, this bit here, as you can see, it goes C, D, E, and then H, I, because this bit is copied from a different part. That's actually comes up in A2 rather than AS, this bit, but may as well include it here because it's just a specific logarithm called the natural logarithm, and then exponential growth and decay. So logs and exponents are very useful because they are the sort of graphs that you will see in real life used for population growth, bacterial growth, and decay in terms of, say, something, a cup of tea cooling, lots of real life situations. So very useful. They used, I remember once, I think, seeing a lesson where it was linked back to logarithms, the logarithmic tables that were used before calculators. Now, because that was quite a long time before my time, I've only seen it once, and I don't have a tendency to use it as a way to show the kids because they have no concept of it. So where I had my parents all the time going, oh, you've got a calculator, I used to use logarithmic tables and all of that. I don't find that particularly useful, but if it's something that you know and love, then you could. But really, I think all it does is, from what I remember, it's multiplying. It's a table to help you multiply large numbers, isn't it? Using the fact that, adding logs is the same as multiplying with, but, well, we will get to that in a minute. It's basically related to the laws of logs. So, this is where I put on the calculator, but Alex, you'll just have to use your brain as a calculator.
No, your iPhone.
So if we think about different exponents, 10 to the 1, 10 to the 2 is 100, 10 to the 3 is 1,000, 10 to the what gives us 10,000. Now, we can see that it would be 10 to the 4. But how would you find
4?
Yeah, how would you find that if you didn't know? That is the question that would come up if this was something really weird. Now, if you type in, in fact, look, what I'll do is I'll do it and I'll hold it up to the camera, see if I can do it. Right, log 10. So I've typed log 10 on the calculator. Right, where's this? No, that way. Too dark, isn't it? Way too dark. Oh.
You keep it still so I can see it.
I know, I'm shaking a load. Right, what I'll do...
I can see it, yeah.
Oh, hang on, here we go. How is... No, it's too dark today.
I'm sorry, lads. I'm sorry.
I'll just tell you, if you type in log 10 into your calculator, it gives you the answer 1. Right? What do you reckon I'm going to get if I type log 100 into the calculator?
2.
2, exactly.
Ordinary set.
Yeah. So, log 1,000 is 3, log 10,000 is 4, because what it's telling us is, so logging it says, what is the power of 10 that will give me 100? What is the power of 10 that will give me 1,000? So it's 10 to the 2, 10 to the 3, 10 to the 4. So you can get the kids to play around with this, logging various things, to find out what the power of 10 is. So another way of writing this is saying log to base 10, so that is our base is our number. This is the power here. So log to base 10 of the number 10 is 1. And what that means is the base to the power of 1 gives 10. As you can imagine, this language is not conducive to making children understand. I'm afraid it is just how we write it. And I tend to spend a lot of time just getting them to write this in equivalent form. In fact, I may have actually done this on the next slide. So you just set them loads of things like this, or you know, whatever it is. You could write 8 to the 2 equals 64. Then in logarithmic language, my base is 8. This is confusing when there's 2 10s, isn't it? And the number is 64, and the answer is 2. So this means log to base 8 of 64 is 2, because 8, the power of 2, is 64. So the initial thing is just getting them to switch between these equivalent ways of saying things. This is the exponent or index way of saying it, and this is the same way of describing it, but using logarithms. And some calculators, the Casio ones that most of them have, the non-graphical ones, now have the facility to be able to type in any logs. It used to be that on your calculator you could only do logs that had base 10. So we used to teach the change of base rule in order to get everything base 10 so that people could use their calculators. But now they can just type in a different base. So if you have that calculator and you type in the log button, it comes up with a little box and you can type the 8 into there and the 64, and then it just works it out. So this is the sort of question, so you might just be given this bit as one of the simple questions at the beginning of the paper, and they just have to write what that is, basically. So they have to think, what does this mean? Okay, log to base 8 of 64 equals some value of x, and that's what I'm trying to find. So we're talking 8 to the x equals 64, therefore from my knowledge of that I need to do x equals 2. So it doesn't require calculators, and they've been trying to move away from these sort of questions a little bit more now that the kids have calculators to do it, because the whole point was you were supposed to be able to convert it into exponent form in order to work this out. Anyway, I'm going to go back to this middle. Move on. Ah, no, we won't move on. You are going to do the same. So rewrite this in logarithmic form. You put your hand up when you've done that. Jerry. Oh yeah, sorry, you're saying sorry for the bit. I see. Yeah, you've done that, Alex? Okay. Yeah, and good. So Alex, what did you get?
Hello. Hello. Yeah. So I got 81 in my head because I have to do it in my head. 3 times 3 times 3 times 3, and then I put the 3 under the log,
Mm-hmm.
and then
Like
81.
Yeah.
4 at the other side.
Yeah.
So
Yeah. Good.
exponent.
You're breaking up. What did you say?
The exponent goes at the other side, so the 4 goes at the other side. Yeah, like that. Yeah.
Yeah. Because what the question is basically is, when I take logarithms, we call it taking logarithms. When I take logarithm to base 3 of 81, what is the power? It is 4. I know that this is it's very weird, and it's one of those tricky things where I think I spend quite a lot of time getting them to just do them on their calculator to see the relationship between power, and then getting them to just switch between these two things in a bit of a rote process, really, in order for them to just get that this is a language issue. We are basically doing the inverse. We are saying we don't know the power. Well, sorry, I was going to cover it up, but you can't see. If we didn't know this, we'd be finding the power. We're just switching between at the moment. Oops. So let me get rid of the writing. So yes, exponential form is that form. Logarithmic form is just as you wrote there. So log to base 3 of 81 is 4. 4 is the exponent. So logs is the inverse of indices. So they're the inverse functions of each other. Now, students find this a bit confusing because it's, when you've got x squared, if you square root it, you get x. But we're not talking about this value here. We're not talking to solve x, we're talking about finding the powers. So you do get kids who just sort of think inverse and see a power and try to root it in some way. But effectively logging is our rooting. So you root when you square because that's what the opposite is. Whereas if you power something, you need to log it to do the inverse. Once they get going, it's absolutely fine. So have a look at these, go down through them and decide whether or not each statement is true. To remember the equivalency, to me, I just think to myself, okay, so it's the base to the power is that. I just sort of like set it up as a little thing in my head so that I know, just to sound listening. Yeah. So the base to what it equals should be that. So just go down and decide if those are true. Mm-hmm. And if it's false, then think about what it should be. Mm-hmm.
I'm missing my calculator.
You don't need your calculator, okay, because these are, well, to be honest, because most of them are false. So, but also because I would say that all of these powers should be things that you know in your head. So, just going through them, well, let's start with the first one, Alex. What do you think that is?
The first one's false.
Yes.
First one's false. Second one's false.
Why is the
Third
second one
one's
false?
true.
Why is the second one false?
Is it 1 extra power?
Hang on, 2 2s are 4, times 2, sorry, hold it up, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the 5 is 32.
I went 60. I went 64.
Okay, that's the 6.
I went on the right. Oh no, and reflection, that one's true.
Okay, good.
Next one's
Sorry,
next
Jerry.
one's true.
Okay, let's have someone else have a go then, Alex.
Then
Have someone else have a go. Jerry, what were you going to say? Is that Jerry? You can, yeah.
10 press-ups.
10 press-ups. Oh right.
Yeah. I think maths and PE go together really well. The next one is false.
Yeah.
So the fourth one down.
What should it be, or what could it be? To correct
it could be log to the base 2 of 4 equals 2.
Yeah.
I looked at what log to the base 2 of a quarter would be mentally, but I just lost interest, to be honest.
Okay,
so I moved on.
2 to the minus
which I
2.
said true.
Yeah, 2 to the minus 2 would give you a quarter. So if that could be a minus 2.
Of course, yeah. I was thinking fractals. It's just going to be a negative. Yeah, sorry.
Yeah,
it's too early in the morning.
Do 1 over. Yeah.
Next one.
10 press-ups. 10 press-ups.
Yeah, I know. But as you haven't done yours, I'm not doing mine. Where are we? So do you want me to carry on? So,
yeah, you can do.
Log of x equals 3 suggests that x equals 81, correct?
Is it?
And then the last two are 4.
4 to the 3 is 81. It would be correct.
I think it's 4.
3 to the 4.
I was thinking 3 to the 4.
Yeah, if they switch the 3 and the 4 around. Yeah. I mean, these are obviously done on purpose. Completely on purpose, obviously.
Yeah. Leaky. And then false and false.
Yeah. I mean, obviously that one's just done as a like multiplying one, like that one was.
Good, yeah. And 256, 16, 64, yeah, 2 log to base 4, 256 before.
Yes, and in fact, what they've done really is switch these two things around, because actually if you had log to base 4 of 4, that would be 1.
It would be 1.
Right. Is this making sense, everyone? Let me unmute you, Evan. Is this making sense? How many people have seen this before?
Just got to get the doorbell.
Okay.
Jogging memories from A-level maths, and
Yeah.
but it's not something I've used since then. But yeah, it makes sense in that it's kind of inversing an indices.
Yeah.
An exponent.
Yeah.
But then
It isn't something that we do regularly, day-to-day life, but it has this massive language barrier for the kids. So just getting them used to all of this. And there's a load of matching cards, which hopefully I've put up in the resources, where you can basically just get them to match together with these different ones that are true.
Sarah, just a moment. I'm really sorry. I've just got the roofing man. I've just got to go and show him where our guttering's broken and birds have got into our roof. I'll be a few minutes.
Okay.
Cheers.
That's all right. So yes, I think this one you can just cut it a bit, switch between, and yes, odd one out that I put on there, so you can just get them to identify what they're doing. And the next step, once they've started getting the hang of just the language and the equivalent meaning between powers and logs, the next thing is that there are various laws to do with logs. In the same way that we can add and multiply and that sort of thing, there are various things that we can do with logs. So if you had calculators, then you can basically get the kids to try just typing loads of different things into the calculator. Or, let me just, I'm just going to, so that you're not just telling them, because it can get really boring. There's all these cards here. I'll start with the numbers. You just cut them all out, and then you give them one of these sheets that you've kind of laminated or printed on card, so they can try putting various ones in. So they might grab log 2 and log 5, put it in the add bit, and then type into their calculator log 8. So if I do on my calculator log 2 plus log 5, oh, I get 1. Oh, of course I do. Oh, if I type log 8 in, I don't get 1. However, if I type in log 10, I do get 1, which suggests to me that log 2 plus log 5 is in fact log 10. Now, if I put log 2 and log 4 in, log 2 plus log 4, that now looks like the log 8 I had. And hopefully they'll keep doing that until they spot a pattern. And then they do the same with minusing and 2 times, 3 times. So this is a really good one for getting them playing around with it so that they discover the laws. Because if they discover it themselves, they will hopefully have it stick in their heads for longer. Here, in fact, are the log laws. So as I was saying, when I was saying log 2 plus log 5 equals log 10, because when you add these two together, the two logs, it's the same as the log of the two numbers multiplied. So we've jumped straight, I might go back to here. So we've jumped. So log 2 plus log 3, I know, is actually the same as log 6. So log 3 plus log 4, what's that going to be?
8. No, it's not. It's not. I take that back. It's definitely not 8.
What is it?
It's definitely not 12 either.
12. Good. Yeah. I'm concerned that you require a calculator to do 3 times 4, but never mind. So equally log 12 minus log 3 is the opposite. Where we were multiplying these two together, we now divide when we have a negative sign. And obviously it's actually just because if we rearrange that, you can see the same. So let us the generic one. Now all of these are written with a little base A. That's just to say that it's whatever the base, provided they are all the same base, it doesn't matter. Now you see on this one, I haven't put any base. If I don't put a base, the assumption is, and this is the language bit again, is that really hiding out there is a little base 10. I just don't bother writing it. Because the convention is that if you write log without a base, it's log to base 10, which is the log that you can use on your calculator. But these rules are true whether this was log to base 70 or 3 or whatever it is. So it is good practice if they want to write the base there all the time, but it's not necessary if it's log 10. So this bit here is just showing our conversion that we were doing before, but all in letters. So a to a power equals c means that the log of c to base a is the power. So that's the bit, the equivalency relationship. The first law is if you add two logs times together. Now I do get, you see a lot of errors where they've written log x plus log y equals log x times log y. Well, that would just be weird, that you could just change that sign to times, that would be true. They've got to take it inside the log, and equally taking away of dividing. Now, if you have got something times log, in fact, I'll put it this way, something to the power, you can bring down the power so that it's k times that. So these three laws, they have to know off by heart at AS level. They are required to be able to do them either way. So they might be given something in this form and have to split it out, or they might be given something on this side and have to bring it together. Why do these laws of logs work? Or why are they these? Think about what logs relate to and what you know about those.
It's similar to laws of indices.
Yeah, it is basically the inverse of the laws of indices, because if we've got 3 squared times 3 to the 4, for example, what do we do with the powers? We add them. That is exactly the same, because if I was to rewrite those powers in their equivalent log relationship, it's the same as this, it's just that it's split out the other way. So when we are multiplying together the two powers, we add the powers. And here, when we are multiplying the two, we split it out to add the logs. So what we could do is log all of this. I don't think I'll bother doing this now. But it is basically the same. I'm just leaving it because I'm not sure if I've left it as part of this set in one of the next self-studies. So I will leave it for now, but it was oh right, yes. And actually it is useful to relate it to the laws of indices so that the students avoid the misconception of that you can do log 2 times log 3 to get log 6. It's only when it's adding because you are adding logs into times these powers. These are the powers. Right. Special cases. Log of 1 is always 0. Log of itself is always 1. And then this looks quite complicated. But again, in terms of y, you just got to turn it back into its exponent form, because this is saying a to the 0 equals 1. So this goes directly back to the indices law. A to the power of 1 is a, so anything to the power of 1 is itself, anything to the power of 0 is 1. This one, if we use the third laws of indices, we're actually saying we can rewrite an nth root as 1 over n. And the third law was if you've got something to the power, you can bring that power down in front. So I can bring that down in front. So it's 1 over n log a. So when you've got roots of things, they end up as fractions in front. I'm not particularly sure that's a necessarily special things to have there. You could work all of these out just on the basis of what you know, all the laws. So what I want you to do is to express these. This is a typical exam question. It says express in terms of log x and log y. That means separate them out using the laws. So let me write out the laws again for you. So log x, y is log of x plus log of y. Oops. And equally log of x over y is just the same. I'm going to do that. So minus that one. And anything to the power, so log of x to the n is n log x. You bring the power down. So for the first one, you're going to want to use this law, which I call law 1, and this law, which I call law 3, because that always runs.
Okay, I'm back.
Hello, Joe. We have moved through the laws of logs, which I've just written at the corner. Basically, they're related to the laws of indices. So you know when you've got, so the base 3, for example, 3 squared times 3 to the 4, in order to work out what that is, you add the powers to get 3 to the 6.
Happy with that. I looked through this because you put it on Student Central, so I'm happy with this.
Oh, great. Okay, so
cheers.
So logs laws basically come from being the inverse of the indices laws. So a typical question is that you're given something like this and asked to express it separately, separating out log x from log y. So you use the laws, and the students find it quite tricky to identify which laws they need. So you've just got to sort of think to themselves, you know, you've got two things being multiplied together. Okay, you've got to tackle that first. So you're going to use this first law and separate those out. Some of them then leave it. So they should show steps too. So I'd want to see that they had done this first. And then they can't leave it like that because it doesn't say express it in terms of log x squared. It says in terms of log x. So you've got to use this third law to bring that power down so that you've got 2 log x. Oops, I didn't say bad, it says log x, plus log 1. So that's just the equivalent way of writing that. That helps because it's easier to work out on calculators. So have a go at doing these. Let me just see what you put. Yeah, well, that's right. So say you'll put your hand up when you've done that. If you've got any questions about it. I can't remember if I've actually already written it. So I think I'm going to write that like that and use little 3 first. As you have to. And then use little 1. And I mean, you can multiply that out if you want to write half log x plus half log y, but it's equivalent. And then this one, you split out first using the second law. So it's division, so you're going to end up with log x to the 4 minus log y to the 3, and then bring down the half. Now, some of the kids can just see these really quickly and kind of think, sort of like, what are you doing? You know, what do you mean steps? They're just instantly look at them. But obviously, in terms of working, they should show this, especially so they don't make mistakes. But any questions about that? You'd spend quite a long time with the kids just getting them to manipulate these different things. And again, there are matching cards where you can match together with the various different ones. Now,
So was that last one incomplete?
sorry, yeah. Go on. Jerry, what were you going to say?
Oh, no, I was going to say the last.
So I can't hear you both talking. Jerry, go first.
Yeah, it's okay. You're doing it now.
Yeah. Sorry, I just kind of skipped over.
That last one was actually complete.
Yeah. There you go.
I was going to have to say that.
Oh, okay. Yeah, sorry, I just kind of skipped through that. But yes, I hadn't finished.
10%.
Is that for me? Yeah, good. Well, you know, at least that means that you are following. So, as I was saying, these laws are true for any base. The base is the little number that we write. And as I said before, if it's not written there, then it's implied that there is a 10 there. Because that used to be the only thing that was programmed into calculators. You could only do log 10. Nowadays, you can get other ones. So, effectively, it's just a little bit about base 10, which creates a, so it replaces a geometric series with an arithmetic series. And that's why they were useful for multiplying large numbers together, because instead of having to multiply large numbers together, you were able to just add them, which is much easier. So, we use logarithms to solve equations involving powers. So here we have a non-exact answer. We do not know what this value of x is. Believe me, the kids will try all sorts of trial and error, even after you've taught them logarithms. They get to the exam, they see that, and they go, oh, I don't know what that is, let's guess. Great that they have some sort of sense of being able to approximate, you know, so they can sort of be like, oh, I guess maybe it's like 5 to the 3, but it's not 5, and it's 5 to the 4. And at GCSE level, this is exactly the sort of things they were given, aren't they? In order to test their trial and error skills, they would try x equals 3 and work that out, try x equals 4, work that out, or think, oh, it's somewhere in between, but nearer the 3, try that out. and keep going until they've got to a certain answer. However, now we don't need to use trial and error. We can work out exactly what this is by taking logs. So taking logs means basically writing log on each side of the equation. I don't know why we don't call it applying logs, but anyway, we call it taking logs. Now, the fact that I haven't written a base is just because it doesn't matter what base log I use. However, because my calculator only does to log 10, log to base 10, I am effectively there is in fact a little 10 here, which I don't need to write. Now, using the laws of logs, what do we know about this side? What could I do with that side? What was the third law? Yeah, thanks, Adam. You can bring down the power. So x log 5 is log 150. Now, this left-hand side just means x times log 5. So it's just, this log 5 is just a number. It's like saying 3x. Which means that to get x by itself, I can just divide through by that number. So I can just do log 150, yeah, over log 5. This is the point at which the kids seem to get confused because they're thinking, oh, it's a division. So I do 150 divided by 5. No, you do not. The log is attached to the 150, creating a new number. You cannot cancel by log. It is something that is done to the number. It is not something multiplying by the number. So we then just type that in onto our calculators, which we all have, of course. Alex. And we get 3.11328. Now I'm sure that I actually typed this in. So let me delete this. So this is suddenly an amazing way of solving things that we didn't know before. And well, what's great is that someone basically has programmed all of the solutions to what log is. So log itself is, as it said back there, it is some crazy series which you would only ever learn about in further maths and beyond, as to what it technically is. As far as the kids are aware, it's just a button that they can press on their calculator. So if you guys now have a go at solving this, and they would expect to see all this working in the exam. So take logs by writing log either side, use the log laws to sort it out, and solve to find n. Yeah, Adam, yeah. Yeah. Yes, absolutely. So if you don't have a calculator, you can still write it as yes. And actually, Adam has just written the answer is, and that is something that they also do. So Adam just wrote the answer as this. And the kids have a tendency to do that, and then really, it's not actually clear what they have worked out. However, as they go through, it should be clear as they do this that they have found n, rather than just randomly putting numbers down. Because they do get confused about what n is, and n is the power. Is that all right? Is that all right, Alex and Jerry?
Yeah, I can get it. I just can't get the pen on. So.
24, so that's about right.
Yeah, so yeah, without a calculator, it's still log 1,000 over log 2. One of the activities that you can get the kids to do is to get an A4 piece of paper and fold it and fold it and fold it. And in fact, that is a limited amount of time that you can fold it in half and reach the point where you can no longer do that. And you can then get them to count the number of layers and the height and plot those on graph paper. And it ends up, being an exponential graph, which looks like this, because it's every time you fold it in half, you're doubling and then doubling again and doubling again and doubling again. So it's increasing by this sort of factor, this base of 2 every time. And so you can then sort of get them to think about that and take a guess at what the equation of this function might be. And hopefully they'll sort of get the idea that it might be 2 to the power of x. The x is the number of folds, number of times that you're folding it. Same with, so SAR is very common. It's the sort of thing where they say, okay, if you're one person, you infect 5 people. Each of those 5 people then infect 5 people. Each of those, so it becomes like a tree that's, each branch is branching out. So you can think about how many times you'd need. So in Southampton, for example, there are, it's quite a while since I wrote this slide, 186,000. It's more like 200,000. But if you were to infect 5 people, they infect 5 people. So it's going to be 5 to the power of something is going to be 200,000, say. So you can find that something just by taking logs. So from the graph, surely that's not, is that actually 200, not 200,000? Okay, let me go back. 2, 5, 2, 5, I'm just doing this in my head.
It's going to be a small number.
Yeah, it's scary, actually, scarily small. In fact, we could just do it. I could just work it out.
I used this in conjunction with that last example you gave in one of my talks, one of my motivational talks on the power of the brain. Do you know how many folds of that 0.1 of a millimeter bit of paper it would take to make the paper thick enough to reach the moon?
The moon?
It's about 64.
2.
Right.
Yeah.
Oh.
It's almost impossible to fold paper after you've done 16 folds in it.
Yeah.
Well, yeah, I'd say, not the fact you only fold it so many times, it's just 42, and if you put in 0.1 millimeters times 2 to the power of 42, it will come to something like 423,000 kilometers, and it's only 380 or so thousand kilometers to the moon. So 423 gets you that change.
Wow.
So there you go, 42. So that your example there is going to be a very small number, I would think.
7.5. Yeah. So basically, 8 interactions is all it would take before the whole of Southampton was in fact infected. So there's no hope for it.
1 or 2 more, because some people might be infecting people that are already, or coming into contact with people already infected. That's not a very clear.
Yes,
example.
And those are the sort of things where if they were to put it as an extra question, they could ask that sort of thing in terms of why. It's less likely to come up in the pure AS and A2, but if you were doing use of math, that's exactly the sort of question they might ask, just to get, to get the kids thinking. It's the sort of thing that everyone complains about because they're like, that's totally unrelated to the math, but it's not. The modelling cycle and the assumptions that we make are very important, and obviously we have to simplify these things in order to be able to model them. and we have to simplify them a lot in order to be able to teach them at AS level. But you're absolutely right. That is a good sort of thing to get the kids thinking about. So yes, the exponential graph starts off slow and zooms up. It so here are the two ones. That's the doubling one, 2 to the x. That's the one where it's increasing by the power of a base of 5 every time. So they are called growth functions because the a is a positive number. So they are going to zoom up. Oh, come on. Hold on. So when we're doing it negative numbers, obviously they're appearing on that side. It's always going to go through 1 because anything to the power of 0 is 1. So it always goes through, the coordinate 0, 1. And then it will keep increasing, basically twice as much each time, like that. So there is our graph of 2 to the x, which of course the kids could work out just by plotting various numbers. But they need to get used to seeing this sort of thing and knowing the properties of it. It will never ever hit the axis, even though it looks like it's going to, it can't, because this is an asymptote here. You can never get 2 to a power equaling 0. It gives you can try it on your calculator, because of course if you want something that gives you 0, that would mean that you'd have log 0, and if you do log 0, it says major error. No, it doesn't say major error, it says MA error, which is like math error, isn't it? So even when it is down this end, it is just in fact very, very tiny. So we try to exaggerate that gap, and I normally draw dashed lines across the axis to show that it's an asymptote, kind of in a red or something, a different colour. But this is just because they are expected to know how to sketch the graphs as well. Now, the graph gets steeper and steeper depending on the value of your A, your base. Very much so, because as you think, this basically is doubling each time. I say doubling, I don't really mean that. It's growing by a factor of 2. This one 3 and 4, so it increases 4-fold each time, 3-fold, 2-fold. It's increasing at a faster rate. So when we look, I don't know if we will look at differentiation of exponentials, but effectively you get the same thing. That is the gradient. Let's see, 0 on that side. Can be anything. It doesn't have to be an integer. If A is 1, you actually just get a straight line, because of course anything to 1 to the power of anything is just 1. So it isn't increasing, it is just flat line. If it's between 0 and 1, so a half x, you end up getting what we call a decay graph. So it still goes through 0, 1, because anything to the power of 0 is 1, but it started up here because a negative number, so a fraction to a negative number is going to give 1 over a fraction, which actually gives you a positive whole number. And yet that then decreases as it goes down. This is the opposite of it. So if the A is bigger than 1, it grows. If it's between 0 and 1, it decays. It can't be 0 or negative, because that is basically undefined, because we cannot take the log of a negative number. That is undefined. Okay, so you're never going to have -1 to the power of something or -2. So, oh yeah, okay, here we are, looking at the gradient. It's increasing, and here are all of coordinates, if we think about the gradient and draw tangents as we go and plot the curve of the gradient function. What do you notice about the gradient function versus the original curve?
Gradients are always the same.
They are exactly the same. Yeah. Which is what I was hinting at previously, that it is the same, basically. That is the unusual, well, not technology, that is the, I suppose, the notion of it, basically, that its gradient, it is a function which has the same gradient as which coordinate. So it is, the gradient function is the same as the original function. Oh, actually, no, sorry, it's not exactly the same, 2 to the x. No, it's slightly different, it looks the same. Slightly different. I'm thinking of e to the x, which is exactly the same. So 3 to the x, so dy by dx is equal to 6, 9. So a log a to the x. Yeah, because if you log the 2, no, yes, ln 2. Okay, so log to base, this is a bit weird because this is log to base e, which I haven't talked about yet. But the same sort of thing will happen with the 3. The gradient function is just above the curve here. So the reason that I'm showing you this is developing into e to the x, but in a really convoluted way. If we do the gradient function of 2 to the x, it is just below 2 to the x. If we do the gradient function of 3 to the x, it's just above. There is, in fact, a curve where it's exactly the same as the original one, suggesting that there is a value of a between 2 and 3 where the gradient of y equals a to the x is exactly equal to a to the x. And this is called E. I think it's called Euler's constant, is why it was called E. And it is the value 2.71. In fact, if you have a calculator and you have a ln button, it looks like in. The kids call it in, but it is actually a little L and then an N. And you do shift of that. You might have to put a 1, so it's e to the 1. You will get 2.71828. That is the value that has the gradient function exactly equal to itself. That is what makes E special. It's using a letter isn't new, it's the same as pi. It's just a letter that represents this number, which goes on and on further. So if we have e to the x, when we differentiate e to the x, we actually still get e to the x. So e is just a number, and it is called the natural, the exponential function. Now, normally when we're talking about log space 10, that's because we've got 10 to the power of something, 10 to the power of x. E is just another base. So instead of writing log space 10, we could write log space e. We're just switching those two around. However, we have a name for that. Logs for the base e are called natural logs. And so we write log space e as ln, which is basically log natural log. So that generally is next to, for me it's next to the log button on my calculator. And all the kids call it in, because for some reason, well, it's because it looks like a capital I. I tend to write it with a curly l to show, curly l, L to show that it is a L instead, and that it's lun, and you call it lun. They'll keep repeating in back to you, so just keep repeating lun back to them. So this is just more language. We have got a new number, e, to a power. When you rearrange that, it's still log to base e, but we write log to base e as lun. How many people have seen that before?
Yeah.
Yeah. You can use, because the log laws apply for any base, you can actually use lun if you wanted for everything. We have a tendency to use log base 10, but lun, log base e, is also programmed into the calculator. So both of those, both natural logarithms and base 10 logarithms, are put into the calculator. So this is the graph of e to the x, and this is the graph of y equals ln x. And I hopefully have told you before that the inverse of a function is found by reflecting it in the line y equals x. Oops. So that's why they are basically a reflection of each other. And where e to the x can never touch this bit, so there's an asymptote here, it's the same here. Ln x can never touch this bit of the y-axis, so there's an asymptote there. So I'm just going to look at some growth order count, just looking at the time, 20 to 11. Should we have a break now before we move on? Until 10 to 11?
Okay.
Okay.
Okay, cool. See you back here at 10 to 11. Cool.
Pardon me.
Thanks for that. Right, let's see how much more we've got to do. Right. How long is your toast taking, Joe? I've just popped down and put the heating on. Absolutely freezing. Right. Just go to the be back. Can I put your hand up to show you back or say something? I know you're here, Alex. There's everyone else here. Yeah, I'm having a similar trouble. You don't have to speak. Okay, so we're waiting on Will and Joe. Toast would be a really nice idea, actually. Can't really eat toast and talk. Anyway, so it seems like I'm talking to myself sometimes and you don't realise because you don't have your question pane open, it's because I'm talking to the people who are typing. Just before you think that I'm weird. I can think I'm weird too, but you know. Well, Jerry and Will can are you back? Cool. Okay.
Just put my headphones on and heard my name.
Okay, cool. Right. Yeah, I do seem to randomly laugh, but I don't know what else who's not listening to the question. Right. So, growth and decay. So, using functions of the type y equals k8 to the t. So, in fact, the variables are is the t. Although it depends. Okay, I'll have a look. Yeah, so k is the initial value because if you put in t to the naught, that whole bit will be 1. So when time is 0, k is your initial value. A is the growth factor and t is the time. So it's either going to be growth or decay. So in the exam, the students are just given questions like this. It actually comes up in A2 more than AS and it's fairly straightforward. I think it's just because generally the concept of exponentials and growth and decay and stuff is considered a bit more difficult. But really, there's not much going on. They're fairly straightforward questions. So A gives the area of a stain. So it's saying at time t seconds, after it had an area of 3 centimeters. So its initial area of the stain was 3 centimeters and it's spreading. So let's imagine you've got an ink blot on some blotting paper, you know, one of those common things that's always around schools still, and the ink is spreading evenly in a Well, it does actually, though, doesn't it? You know, if you put a link block on it, it does spread the circular motion. So the value of A is the growth factor, and it's 1.4, so we know that it's going to be a growing strain. It would be weird if it was a diminishing strain. Here we've got the mass of a radioactive element. They love to do that because the thing about radioactive elements is they decay. Sorry. No. Oh God. Right. Sorry about that. So they often ask things such as, what is the half-life? Which has got to get the students understanding about radioactive elements. It's one of those things that you would need to show them so that they appreciate that a half-life is when the mass is half its initial mass. So in this case, initially our radioactive element has a mass of 500 grams and it's decaying at a rate of, at a rate of 0.8. Sorry.
Sure.
Thank you. Sorry. So it's decaying. So if you wanted to know the half-life, that would be when the mass is equal to 250, or when the 0.8 T is a half. Anyway, I think I might do one of those later. Compound interest, another great growth, exponential growth sort of thing, where, well, I wish it did grow that much. Oh dear. So you initially invested £400. It's growing at a rate of 5% each year. That would be fantastic at the moment. So here we have the mass of a baby, which is fairly exponential initially. So find the mass of the baby at birth and the value of the growth factor if m equals 3.48 for t, and if the baby has a mass of 6 kilograms at 10 weeks. So it's fairly straightforward initial question, the mass of the baby at birth. Is this in kilos? Yes, yeah, that's fine. Yeah, that's about right. So just what, about 7.5 pounds or something, 3.4 kilos. So when t is 0, when the baby is born at 0, this is 1, so the baby weighs 3.4 kilos. Now if we put in the other bits that we know, the baby has a mass of 6 kilograms at 10 weeks, so we know that m is 6, t is 10. So here we have basically everything known apart from the A. So we can solve this to find what the growth factor is. So we divide through by 3.4, and then we've got a to the 10 equals this. So we just have to, well, basically 10th root it, or do it to the power of 1/10. So this is not a logarithm because we know the power. We are basically trying to find x. This is a traditional solving. And that's where the kids seem to get confused, because we've been talking about taking logs and all of this stuff, and suddenly they're presented with a very straightforward equation that they can solve, and they start taking logs and all sorts. So the growth factor in this case is 1.06. So they are giving you things that are related to exponential functions, but you're not necessarily having to use logarithms to solve them. So you're going to have a go at this one. Find the time taken for a cup of tea to cool to 60 degrees Celsius if it's given by this. Now I've just been a bit mean because I've been telling you the previous one you were having to find the growth factor, which was the x. Now you are being asked to find the time, which is the power. So you're going to need to use logarithms or something. So have a go at solving this. So I'm going to click through and show you. So we know that T is, capital T is going to be 60. So that's our starting point. Before you can log anything, and I should have said this, it has to be by itself. You can't log this with these two bits. You can only log the bit that the T is attached to. You've got to divide through by 80 first. Then you can log so take logs. Again, doesn't matter if you use base 10 or base E or whatever. So we've logged it. We use the third law to bring down the power of T. So T is just log of 0.75 over log of 0.94, which is 4.65. So it takes 4.65 minutes to cool from its initial 80 degrees to 60 degrees. Have I gone through that too quickly, or did that make sense?
That's what I got.
Good. Will?
So, yeah.
Yeah. Alex?
It's a bit steep for me, that.
At what point? Is it the lack of calculator or beforehand?
I think reorganising it's confused me a bit.
Yeah, and that's why also with the students, you know, you would spend at least a lesson just playing around with the laws of logs, so that you start to recognise that if you see something like this with a T, you want to bring it down in front, and that helps you because that's just T times something, so you can divide through. And you just do a lot of practice of these. In fact, I think I've got more for practice. Yeah. So, again, this is what I was talking about before. Half-life of a radioactive element. This is a model. I mean, and this is A2, so we're talking A2 level. So it's fairly hard going for a Sleepy Friday. The half-life, we haven't been given anything about M0. It's just called the initial mass. You don't technically need to know, because if this was 500, for example, then the half-life would be when the mass here equals half of that, so 250. So as we divide through one by the other, we'd get 250 over 500 is our 0.99t. And 250 over 500, or whatever numbers I had chosen, would give you 1 over 2. So your starting point is going to be that you've got a half is 0.99t. So that's what it means to find the half-life. You're going to find when this growth function is equal to a half. So from here, so that is the first thing the kids need to recognise, that a half-life means doing this. And I suggest them often to sort of do, you know, make up things. make up values just to check that they figure out that that is a half. Yeah, so log both sides. Kind of a very relative estimate of put all the end notes on this. Yeah, yeah. So take logs. So take logs, bring the t down using the third law, and then divide through. So yeah, 68.97 or 69 years. So once you get into it and they'd be practicing this for quite a long time, they would, get used to this process and start to use log just like it's anything else that you apply. Any questions about growth and decay questions like that? Will?
No, that makes sense. Essentially, it's just using the log to actually take the exponent down to being just a coefficient, and then you can work out what that is.
Yeah, I mean, ultimately, it's just like solving any equation. It's just that it's all wrapped up in a real-life model. So the kids have got to, which is why it's put into A-level, really, because they've got to extract, or A2, they've got to extract what is happening from the information they're given, and they find that incredibly difficult. So we've got this sort of word question that they have to interpret. Then we've got this, all this new vocabulary of sort of using logs and that kind of thing. And then recognising that you've got to use these laws and solve it to work out the answer. So they're often given basic logs that they're expected to just muddle around to say what they equal using the log laws. The equivalency, switching back and forth. Growth and decay problems like this. And the final type of question they're given is something called reduction to linear form. Will, can you just mute your microphone, please? Will, sorry, can you just mute your microphone? Okay, thank you. Reduction to linear form, very useful for simplifying things. Seems a bit weird, but it works. We think that we've got a set of values, we've done an experiment, we think that they are related, and that their relationship could be a straight line. But, no, that's not what I said. So we think that it might be something to do with exponents, so some sort of exponential relationship. Now, these are slightly different because really helpful when I've done an N instead of a B there. That's not helpful. That's supposed to be B. Anyway, there's two different forms here. This one here is a polynomial because we're saying that the value of x changes, but the a and the n, which I meant to put the b, they are constants. They do not change. So this could just be x squared, or it could be an x cubed, or an x to the fourth, some sort of polynomial relationship. This one is an exponential. You've got a constant that's to a power that is changing. So we've done an experiment, and we think that it might be a polynomial graph, or it might be an exponential graph. If we use logs, if you think about the way that the logs worked, it kind of does the inverse of the powers. So it can, so when you apply an inverse to a power, it flattens itself. I think about it. It undoes what's happened. So you're back to nothing. Well, not nothing, but it undoes what's been done. Let me show you what I mean. Let's suppose we think that we have a polynomial relationship. So I've got some function that's relating x and y. And x and y could be anything. It could be that I have... Jerry, did you want to say something?
Yeah, I was just going to say, it's summed up by the statement you gave earlier on, which says it turns a geometric sequence into an arithmetic one, giving you your straight line.
Exactly. And this is particularly useful in science experiments. So a lot of the kids, when they get to you in maths, have used this in order to, they've done some chemistry experiment. And they're like, oh, yeah, we've done this. I've seen this before. So they've done some sort of experiment in class, and they've taken readings. So maybe they have, I don't know, set something on fire and then measured the weight of the remaining ashes over time. I have no idea. And they think that they've got a load of data. They think that it might fit some sort of polynomial. Now, if you take logs on both sides, then use the log laws to sort this side out. So we've got two things multiplied together, so we can add them, and then we can use law 3 to bring this power down. What I've done is what we call reduced this to linear form. So this has become linear because I don't have any powers in it. It is something that I could describe in terms of a straight line. So what I'm just doing here, I might actually have already done this in a slide. I can call these a new variable, which I'm going to call capital Y and capital X. But basically, the straight line has the form y equals mx plus c. I can look at this and compare it back to my original and think, okay, my variables were y and x. So my variables are still going to be the things involving y and x. So your y is going to be log y now, and your capital X is going to be log x. Now, if you think about y equals mx plus c, the gradient is the value with the x. So your gradient is going to be represented by the constant n, and your y-intercept is going to be represented by log of the constant a. So that's the same what I just said. So this is a little process that the students need to learn, that they will get used to once we've got past this initial bit. Now, I have said I've done it this way, but I think I have a handout that I've attached to the to Student Central that I always used to use, which is about 110 mink, which should happen in 1966. So apparently 110 mink escaped from a farm, and then they monitored the population of mink in the area. And what I get them to do is saying, okay, plot that original graph. So they plot the original graph and they think, okay, it looks like it might be exponential. And then we're like, okay, well, to check this, let's try doing log of it and see if we get straight lines. So going back to this. So what that means is if we look at our original values we have, we would have had a table of values which had x and y. Now, what we want to do is draw a straight line of our new x against y. So our new x is log x and our new y is log y. So we need to take our table of values with x and y and log both of those and then plot them. So here is our original table of values. We want to log both the x and the y and plot them against each other. And when we plot them, you can see it is almost a straight line. So we then draw a line of best fit through those, and that means that I can then calculate the gradient and the y-intercept. So the gradient is roughly 1.7, and the y-intercept, we can't see because it doesn't go down to 0 in this case, but we can calculate by putting in two values of the gradient. And they end up getting that it is 0.3. Generally, you draw a graph where it went, you could extend it to y-intercept. So we now know m and c. And if we look back here at what those were, m is just our value of n. So we have found n straight away. We've found our power, which is 1.7. C is actually log a. Now we want a. So this is our straight line graph. We know that n is 1.7 and log a is 0.3. So just using the equivalency, we know log to base 10 of a is 0.3. So to get a, we need to do what is called anti-logging, converting it back to the equivalent exponent form that a must equal 10 to the 0.3. So 10 to the 0.3 is 2. So we've now got all the values we need. Oh, how do I go back? Now, what it hasn't done is what I always say to the kids that they must do, because the whole point was they were trying to find a relationship of the form ax to the n. They should therefore state that relationship very carefully now that they have found a and n. So a is 2 and n is 1.7. So going back to what we are doing, we were looking for a relationship. We were looking for what function related our table of values that we had here. So we imagined that it was of the form y equals ax to the n. And in order to figure out what a and n were, we were able to use logs to reduce it to a straight line so that we then could plot the graph of it, work out the gradient and the y-intercept, and use those to find our original values of a and n. Then we were able to write out the relationship. So it's a bit of a weird one, but very, very useful to avoid having to guess. I think that would be the only other option. Now, it doesn't give you an exact fit, of course, because it is just a model using values. And you've drawn your own straight line, which could be, slightly different. There's a line of best fit. It might not be the exact one. Now, this is the exponential form. It just works out slightly differently. If we take logs and use the first law to split them out, and use the third law to bring down the x, what you notice when we compare it to y equals mx plus c is the y is still log y, But our x is still just a variable x. We don't log x in this case. Instead, our gradient is given by log b, and our y-intercept again is given by log a. So we've got the values x and y. We only have to log y this time and plot a graph of x against log y. The kids find it very hard to understand this bit and to appreciate what it is that they need to be logging. So they have to really think about what a constant is and what a variable is. A and B are constants. They remain constant. If you log them, they are still constants. Whereas X and Y are the things that vary. And that's what you need to plot. So, we plot log Y against X. And you do the same thing. You then draw a straight line and so forth. So, if it's a polynomial, you end up plotting log y against log x. If it's an exponential, you end up plotting log y against just plain x. Oh, and I thought I was going to get you to do some of it, but I think it was too tricky for me to get
Too
you to
late.
do it. Too late. Bye. Yeah, quite. Oh, I've lost the webinar page. Where's it gone? Yes, so I'm just thinking, where is that? Where's that sheet? No, no. What I would recommend is that you guys have a look at these and have a go at doing them, because it's quite tricky. Now, you see this one here. It says, one day a chemist collects the data below. There's text of data here, T and A in this case. He thinks the relationship might be exponential. Show that he is correct by drawing an appropriate graph and use this to find the exponential function which models this relationship. That would be incredibly tricky if that was given as an actual question, because the kids would need to come up with what the exponential function was in the first place. They tend not to do that. They tend to say something like this: the relationship is believed to be of this form, so they give them some sort of form that they can then do the reduction to linear form on. So it says that P and Q are the constants. So P and Q are the constants. Okay, that doesn't seem quite true. I'm going to change that, because that should definitely say variables. Here we go. So the one that's on that I've got as student central, I'm afraid, is wrong, because that should not say variables, or it should say where A and B are constants, in fact. Sorry, that one's incorrect. But A and B are the constants. So things that are constant the whole time. You can find those values. So you log both sides. Estimate the values of A and B. So the difficulty with me trying to get you to do this now is that you can do that first little bit where you're working through it, doing the reduction to linear form by logging it using the first law, using the third law, comparing it to y equals mx plus c, but then you have to draw a graph. There's no way around it. You have to draw the graph. You'd have to log all of these, draw the graph, and then draw your line of best fit, find, this is a very involved question, and often come at the end of the paper because they're fairly involved. But have this very strict process that the kids, once they get it, are quite fine to do. So I would recommend working through this sheet yourself as a way to further practice this. because it involves, it just involves a lot of graph work and plotting things. So if we just go back to going back to what you need to know, sketching the graph of A to the X. That is an understanding how the different values may affect the shape of the graph. So we were looking at the fact that when A is bigger than 1, it's growth. When A is between 0 to 1, it's decay. It always goes through 0, 1. The relationship between logs and indices is that conversion, that equivalency relationship. And there's the 3 laws of logs, excluding change of base, which we don't really teach very much anymore. It is, I think, in Excel A2. But less necessary nowadays with modern calculators. Use logarithms to solve equations like that. Understand the properties of the exponential and logarithmic functions e to the x and ln x. So e to the x is the value, e is 2.71, and the property of it is that its gradient function is exactly the same as the original function. Ln x is the reflection of it, and is just the natural logarithm of it. And understand exponential growth and decay. And I actually haven't put on there about reduction to linear form. So we've covered AS and A2 work for logs and exponentials. And are there any questions?
Is there an answer sheet with that question sheet?
I don't think there is, because I always did it in class. So that I then did it with them. Let me see.
You can make your own, Alex. Wink, wink.
Well, okay, I'll do that tomorrow.
You can do it and, share with us what you got, and then we'll tell you all wrong,
I might give it to my mentor. I might give it to my mentor to mark.
Yeah, that's true. You can check it by putting the values into autograph and right-clicking and choosing line, exponential graph, and seeing if it's the same or similar. So I'm just seeing if there's others that have good models that have any answers.
Sorry, Sarah, can you just remind me, autograph, is that an app that you told us about earlier in the year and maybe gave us logons to? Because I've lost the notebook that I had a lot of the really early stuff right from the beginning of the course.
Oh, right. Can you access, on Student Central, you can still access your previous year, can't you?
On Student Central, yeah. Is it on Student Central?
Yeah. Let me show you.
Where will I find it?
I will show you. Can you now see my screen logging onto Student Central? Yeah. So in studies, last year, so your subject order development last year's you there, isn't it? 2014. It looks different, obviously, to yours.
Yep.
And go to study materials.
Okay.
Yes, let me think. Did I do it as your first ongoing activity? Yes. So it's your first ongoing activity. I know it's not very useful, is it? Because they're not titled stuff. If you compare these names to the spreadsheet, but anyway, in ongoing activity 1, there's a bit about autograph there. And you can get a 30-day free trial, basically, on the autograph.
Right, okay, I didn't do that.
If you're rather than searching through all of these things and figuring out what they are, because they're just named after self-studies and stuff, in the key documents is the spreadsheet which will tell you what each of the things are.
Okay. How much is autograph once your free trial is up? Is it worth having?
I would say it's not worth paying for it when you can now have GeoGebra for free. You know, no point paying for things that you can get for free. Very different, GeoGebra and Autograph. GeoGebra is a dynamic package. Which is probably more modern day. So yeah, totally. Rather than using that, you can just do this. Okay, I think I pulled my tweets out. What's it doing? It might prefer it in Chrome. Okay. Yeah. What is it doing? I don't know why I keep having issues with GeoGebra. But let me show you Autograph briefly. I nicked a copy from school years ago on a CD, so I've got quite an old version of it, but it's my Firefox.
Sorry, so is it an ongoing subscription, or is it just a program that you buy?
Yeah, it's just a program you buy, so your school might have a CD of it. I use them for different things. GeoGebra is excellent for getting the kids to discover things because they can move things around. They can draw a graph and then pick it up and move it around. If I could get it to work, it'd be really good. Yes, it's in materials actually. It may just be that I need to download it properly. I want something like this. And
one other question while that's loading.
Yeah.
Does the university have a My Maths subscription that we can use?
Not that I know of. I will ask.
Because that's the most useful thing I've found of all of these resources. But now that I'm not at my school, I think I've been locked out. They've locked me out of everything else.
Oh.
You know, you can use My Maths lessons without a login. You just need, you can just go on the website. You can't do homework activities without a login.
Can you get all of them? Because I know on Maths Watch there's only a couple of things you can get. I've only used My Maths with a login. So can you actually get all of the lesson content then?
I think so. If not, drop me a message on Facebook and you can filter my school login so that you can actually see all the lessons.
Great. Cheers, mate.
And you've got login from me for the integral resources, which has got all the material you need to tell you more, like more notes for you for knowing more things. And there are some resources in there. So here's GeoGebra. I can pick things up. Maybe I can't because I haven't actually got it. Maybe I just change these things. I can change things, and it will change things.
Can you change it from Russian?
I know that is a bit of a problem with this one, but you can find all sorts of things, and you can get the kids to investigate stuff. Now, so that must be changing the gradient, you see. So they're changing a gradient of a straight line, and they're watching it do that. So it should start to suggest to them, oh, when it's positive, it goes that way. Or when it's smaller than 1, oh, negative. So it's quite good for getting them to investigate things, GeoGebra. You can write it from scratch yourself. I have never done that because I do not know how to. There's a massive guide that I tried to figure out once when I tried to write something. But generally, you can find anything that you need to. Oh, Catherine's written this one. Sorry, I just know Catherine. Oh yes, great for getting them to do the circle theorems themselves, because look, lovely. Catherine is really good. She's the MEI expert on all things technical, and she's very good at writing a lot of GeoGebra stuff. And she posts all of these in the integral resources, because she works for MEI, who make the integral resources. So that's quite good. I wonder if it does each one of it. Angle in the centre. It's not changing. If I drag this down, there we go. Ooh, nice. Subtended by the, what can I change? Ta-da! Oh, I like that. Very nice. So, GeoGebra is excellent for dynamism, being able to move it. Autograph is not. You cannot move it. Autograph is static. It just gives you a graph page. It's really good if the kids are doing some sort of project and they want to print beautiful looking graphs, or they want to plot table of values so they can enter a load of data. So this is really good for the kids who are chemists or whatever, and they have data of their own that they can put in here. They can then draw it, and then they can, in fact, if I put something in, I should open something, but so okay, so I plot that. There it is. I think to myself, oh, I don't know, that could be a quadratic. It could be exponential. Let me see by selecting all the points. Actually, can I just do it by right clicking? Select all points. Right click. Oh no, I got it. How do I select all points? Select all points. Right, I've selected all the points, I've right clicked, and now I can get the best fit. So they seem to be thinking that it might be a polynomial of order 5. Well, what if I do a polynomial of order 2? Oh yes, I see that. Why they don't think that. Okay. So it's quite good for lines of best fit, especially if it's straight lines. So let's try best fit again. So they think a polynomial of order 5. Oh, that is good. Look at that. So that is a polynomial of order 5, so x to the power of 5 in some form. And if I click on it, that, can you see down here, that is the equation of that polynomial. So that, I mean, if you were a chemist, you put in a load of values, you wanted to know what the relationship is, that is the relationship that they think is the best fit for those points, as it really is. I mean, that's brilliant. So autographs, just very different. You can do a lot on it, but I've never really learnt a huge amount on it. You can get 3-dimensional drawings and all sorts. It is most useful for stats. GeoGebra is a dynamic geometry, whereas this, you can plot statistical graphs on stuff. So I would say autograph for best fit and statistical graphs, and GeoGebra for everything else that involves geometry and graphs and any sort of discovery. So getting graph, anything that here, graph transformations are best done on GeoGebra, because, so if they want to do a stretch of something, now what's annoying is if you have the actual program that's not the online version, then, so if I had downloaded it onto my computer, I can just use my mouse to drag things around, whereas I actually have to change these, but that works fine, doesn't it? So again, they're looking at a stretch, they can see what the effect of the stretch is. And if you want to see what it is, you can change the function. So I can just double click and I can change that to, I don't want to change that bit actually, I need to change maybe that bit. So I change it to an x4, and there you go. It's given me a quartic graph now, and I can still change it just the same. So I think you would be better off learning GeoGebra, because actually, how often do the kids in our maths lessons need to know line of best, do fitting, unless it was very common. It is common with use of maths. Autograph is more useful because they have to do a coursework where they have to identify the model that fits their data. But in traditional maths, we don't tend to do that, and thus GeoGebra is more useful. So there you go. That was a little bit about that. let me talk to you about your assignments. I've just sent you this. I sent you this just before we started the webinar. This is basically what Carol has now sent out as her guidance for your assignments. They are due on the 14th of March. Excellent. It's not like I'm busy then. Anyway, there may be some delay in marking them, depending on, since my dissertation is due on the 27th of March. But anyway, so they're due on the 14th of March. I guess that's probably Friday, but I don't know my calendar. It's exactly what we talked about before. You have got to deliver a 15-minute presentation, but instead of it being at the ISW as I originally thought when I very first saw you, we're just going to be doing more learning then, which I'll have to make up since that's extra to your actual course that you so far. So you won't be presenting to us then. Instead, you are going to be presenting in a mentor session or a departmental meeting or something like that. So your first thing that you're going to need to do is share this with your mentor and get this penciled in for sometime next term. So you are going to deliver a 15-minute presentation and they need to give you feedback. So ideally, if you print off the teacher's feedback form and give it to each of them, then they will fill those in. Or they can just give you feedback and you type it onto a form that you're going to then submit as part of your assignment. So it says, following your presentation, you will reflect on the feedback and add appropriate comments to your work. So you can effectively make what you send to me as perfect as interesting as possible in order to tick all the boxes. So you then send me the presentation, PowerPoint or whatever it is that you've done. Most people do a PowerPoint. The commentary, that is the key bit from which I can get the marks, from reflections, and that's the feedback, really, the reflections and feedback. So the feedback from both school colleagues and subject tutors should be used to help you develop a subject knowledge action plan for the final assessed teaching phase in the summer term. I need to get back to Carol about whether she wants that submitted to me or her. Right, I know. So we talked about this before. You can either choose one big thing and talk about it, something that's impacted on you, whether that be girls learning maths or developing growth mindset or whatever you want. Or you can select 3 resources or activities that you've done. Now, what we found was the people who selected 3 resources, in order to get the depth and critical, the critical theory and stuff into that, they couldn't really fit it into the 15-minute presentation because 3 things sort of going into depth. Now, technically, that doesn't really matter because you're not submitting to me. I have no idea how long your presentation takes. Obviously I'll see a bit of feedback from them, but ultimately what you submit to me will have the theory and all of that in it. So you can include that depth and analysis even if you don't say it in your presentation. So it's up to you. You can either choose 3 resources or activities, or you can choose one specific thing that you want to talk about. If I open up Cohort 1 assignments, just wondering what to. So here is what Ewan submitted. This is his PowerPoint. He looked at teaching strategies in maths. I don't know it's so small. So he submitted this to me, which was his PowerPoint. And as you can see, because he basically talked about each thing. So the PowerPoint itself, I didn't mark particularly. I could see his notes. But the presentation itself is slightly taken into account, but not really. But it definitely should have references at the end of your PowerPoint. And as you're talking through this, you should be referring to those. So according to Colt's experiential learning, you should be doing la 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 la, that sort of thing. Like he's putting a group vitally important, Bowler 2008, blah blah blah. So that was his presentation, and his thing that he submitted to me looked very much like it's kind of like an informal essay, you know. So it's talked about that, and this is what he said. He had his PowerPoint. He had this on the screen in front of him, and he basically read it, but he knew it pretty well. But it's all fine for I wanted, blah, blah, what he's done. So he's put in the literature and looked at, you know, he's got his quotes from things. But it's just a bit more informal because you don't have to write it in proper sentences and proper paragraphs, because it is your commentary that supports the PowerPoint. So that is, I'm just going to show you Dave's, because Dave did 3 resources, but it was all a bit much because he'd done a whole thing where he had developed mindset, in fact, and so he talked a lot about that. And unfortunately, he then barely got onto his other 2 resources, which was about how to get kids to describe things. And then he talked about how he'd gone on about using these. So he'd sort of used these things, but he'd included his theory like this. There you go, experiential learning. And talked about it. And then in his commentary, again, that's just basically what it was, notes to himself about what he's saying. So it's, as you can see, it's just less formal. It doesn't have to be, and it shouldn't really, I suppose, be in any sort of essay. But the kind of thing, as you write it, you see, look, critics such as Merriam-Webster suggested these, la la, I believe this, la la. So, does that make sense?
What sort of word count are we looking at?
I think it is 3,000 words. Yeah, 3,000 words. It means equivalent to 3,000 words. So I'm not going to be counting it. But if you go on longer than 15 minutes, you probably have gone over the word count.
Yeah.
So I think that was more the accuracy. That if you write your commentary and you say it, and it's kind of within the 15 minutes, give or take, then you've got about the right length.
Cool. Thank you.
It's all right. Any other questions about it?
I showed this to my mentor, and he's already set a date for me. Unfortunately, the date's the middle of January. So.
Oh my God! So you're
I'm not too concerned. I've already been thinking about it, and I've probably been sure on some stuff I've done for the last episode. But,
well, yeah. At least it's done then, I suppose.
His thinking was it was basically going to be in the maths department meeting in January or the maths department meeting in February.
Right.
I think the February ones during the ISW.
Yeah.
And it wouldn't have given me much time to sort of improve upon it from where he'd from their feedback.
Yeah.
It's quite daunting because there's got 11 teachers in my maths department, and some of them have been teaching maths longer than I've been alive, so it'll be interesting. But yeah, it'll be good. I'm not particularly concerned about the time scale on it, actually. Obviously.
Good. Okay.
That'll at least mean that it's pretty much done and dusted well before the deadline. I can just hand it in.
Yeah, absolutely. I better set up a submission appointment. But yeah, in terms of like their opinions of things you could have done better, you don't have to take that on board in terms of, you know, changing your commentary and stuff. But if they say things like there wasn't much theory to back that up, or you didn't say enough, we wanted to know more about why you thought it worked, that sort of thing. Those are the sort of things you want to be adjusting in order to hit the outcomes. You know, demonstrating this, analyze, critically reflect, and engage and analyze the relationship between theory, policy, and practice. And I guess it's worth giving that to all of them that are going to be attending. Yeah. Otherwise, that's it really.
I've got a couple of very quick questions.
Yes.
You talked earlier on about autograph and, you know, printing out graphs. Has anyone got any resources for making specific graphs and position and axes? Because when I have to print stuff off, you know, so my girls aren't spending a whole lesson just drawing a pair of axes nice and neatly.
Oh yeah. So, yes, that is what I use autograph for.
Okay, so right.
Yeah.
But that's okay. Has anyone got any free ones where, you know, because there are things you can buy graph or you can download graph paper, but then you've got to piss around putting lines on it. Does anyone know of any apps where you can just make resources like?
You probably can from GeoGebra as well.
Okay, I'll have a look at. Okay, that's enough. Then I'll look at GeoGebra. And there was one other thing. That calculator you showed us, Sarah. I've got something similar, but the colour version. Is it possible to use that as a calculator? Because the one I've bought was a Casio FX CG20.
Oh yeah,
all sing and all dance, latest thing.
Yeah.
And I'm bugging if I can find how to just like put in, you know, 5 times 5.
Oh yeah. Okay. You know. On the menu. Oh, hang on. Where is it? There we go. It's too dark in it. Can you see the one that's highlighted, which is called Run?
Run.
Yeah, Run.
I've got Run Matrix.
No.
That. There is one that's just called Run.
Okay, we'll go into Run Matrix. Okay. Does it look like? Is it a blank screen?
Ish.
Ish.
Yeah. Okay. Look at that one. It's got some stuff in there as by way of examples.
Okay, that's weird. Go if you got a menu button.
Yeah.
Press menu.
Yeah.
Yeah. So how many of those have you? Sorry.
I've got. I think I've got 20.
If you scroll up to the top corner, is there nothing that's called Run or?
Yeah, just Run Matrix. The top left-hand corner.
Then I think that must be it, because normally it's if you also press 1, it gives you that. When you're on the menu 1 gives you for me I have a blank screen and I just type into it.
Okay, yeah, it looks like that might work. Okay, good. I was just a bit perplexed. I've played with it a few times and it does some wonderful stuff, but I couldn't find the page that did that. I think it's because it had set it up as an example of something quite complex. Okay, good. That's it. I went to all the time. I'll mess around with that screen.
So in terms of what we are doing next, I think I've got a self-study for you next. So today is the 30th of November, so we've talked about exponentials and logarithms. So your ongoing activities are supposed to be considering theories of learning and investigating ways to improve students' mathematical problem solving skills. Okay. That's just what I put. Whether you do it or not is just to aid you with your ideas for your assignment. But 7th of December, we've got a self-study, which is exponentials and logarithms. And other than that, there's nothing until I see you the week of 18th of January for some trig. So yeah, it's been very few and far between this year. I don't know why. So we've got the ISW in February, but I will see you once in January, and otherwise that is it until sort of towards the end we have a bit more. But what was I going to say? Oh yeah, I'm just going to check whether I have yet put no, I've obviously shut Student Central. I was going to go back to Student Central and see if I've put up the study. But anyway, my next thing will be that I will put up a self-study, which is all about this exponentials and logarithms. And in fact, that will be hopefully enough to develop the materials. No, I haven't yet put up the next self-study task. So that's my next job, is to put up the self-study task for you guys. For exponentials. So this is what it will be. So there's a lot on there, in fact. So there's a couple there for you to do for the reduction to linear form anyway. So you could just do all of that, and that would be sufficient. Equally, I haven't done an answer sheet for that either, but I can do. In fact, I think I have copied these off that other sheet. So I will upload that to Student Central. That is your next thing to do, and your assignment. And otherwise, that is it. So, any other questions or anything?
No, thanks, Sarah. Next time I will, I'm on mute. Next time I'll bring a calculator.
That would be a good idea, because we're doing trigonometry, and you are definitely going to need a calculator for doing all the sine and cos of things, I think.
And I've done about 200 press-ups so far.
Well, that's all right then. At least, you know, you're improving.
Just as an aside.
I thought about mine, and it's the thought that counts.
Oh, it's the thought that counts. Okay, great. Will, what were you going to say?
I was just an aside. We had a big crackdown at school this week on kids bringing like kit to maths lessons, and we gave out current total stood at something like 95 detentions out of 900 students for not having the right equipment.
Wow.
So,
I consider myself told off then. Okay, I am on
Told off, mate. You're in detention.
Well, you know, you've only hurt yourself really, because I'm afraid it's you that doesn't fully understand. Because you weren't able to experiment.
Let yourself down. Let yourself down.
Mate,
anyway.
I can thoroughly recommend going and spending a month's student-teacher salary on one of these calculators, mate. They're ace.
Yeah, I couldn't live without mine. I love mine. I nicked mine from college when I left, and it was the best thing I've ever nicked. They are 60 to 70 quid on eBay or Amazon.
Mine was 120. Have I been ripped off?
Well, yours is obviously all singing or dancing. It just depends on whether you really need it to be that much singing and dancing.
We're all ex-military personnel. We need the best gadgets money can buy.
Okay.
If they're no use.
I use probably use 1, 2, 3, 4, 5 functions. 6 maybe out of the. I mean, I've got 15 and I use 6, so I don't even use half of all the things that I've got in my menu. And you said you've got 24, but you're unable to use it as an actual calculator. So perhaps you have brought beyond your needs.
No, I can now use it as a calculator. I've just been messing around with that. But no, I think there are probably 10 of them I'll use.
Yeah.
And it's got one called Physium, which has got the periodic table. It's got all sorts of. It's got pretty much every table of science, functions, notation, laws. It's got a conversion function on it. There's loads.
So obviously they wouldn't be allowed that in your one. It wouldn't be allowed in any sort of science exams. And also what we do when the kids go into exam is we clear the memories, go around clearing the memories off their calculators, because you can store absolutely everything. So they can store the quadratic formula and anything that they want to remember. You can just type.
What?
You can type.
On an FX85, can you do all that?
On my one you can. Oh no, mine's a 9750. FX85, that's probably.
FX85 is the one that all the exam boards recommend the kids in GCSE buy.
Oh yeah, no, not.
Smith and Sainsbury's.
Oh yeah, no. Sorry, I meant the graphical ones at A level. At A level, we go around deleting all their memories on their graphical calculators if they have them.
Yeah, you can clear the memory in the graphical exam.
Because they are basically computers. You can type anything in.
Sure. No, they are. I thought you were telling me something I didn't know about the FX85.
No.
Bastards are using them.
No.
They know something about it. I'm going to be really pissed off.
No, but what I do find is that with these ones is that the kids, the bored, under-challenged boys who are seemingly a bit thick are sat at the back of the class programming games into them. And I'm just like, seriously, you're failing maths, but you're programming games into your calculator. You just really need to employ those skills better elsewhere. And you can get, have you got all the connectors, the leads that can connect it to whiteboard, screens, computers, and everything?
I don't know about whiteboards. I'm not really much of a geek. Interactive whiteboards are something I've never.
Yeah.
But yeah, there are some leads that I need to look at the utility of.
I think just connecting it to a computer, then you can show what's on your screen, which is useful if you ever want to use this. If you're ever teaching International Baccalaureate or use of maths, for which it is expected that they are very much at ease with these, then you can be typing on yours and it's projected on the screen, which is great. Anyway, I will leave you to. Is there anything else that anyone wanted to say?
I think so.
No, okay. Well, do you guys want to chat to each other?
I'm easy.
Well, we've all got essays to finish off for Monday, so.
Oh right.
We're going to tackle with that.
Okay. Have fun.
If you do want to talk to me, that's fine. I'll just move on.
Nothing personal.
Right. Oh, let me stop the recording.
I need to go put